Now to look at the effect that this force will have on a particle. So let's start by looking at the picture on the right, and we're going to look at that positive charge that is down the bottom of the circle. So it's moving to the right, and the field is acting into the screen, as we can see from the crosses. So using our right-hand rule, your thumb points to the right, and your fingers point into the screen. Try it right now to confirm this. Your palm should be pointing upwards. If it's not, maybe you're using your left hand. So that upwards force is going to divert the particle's path to start curving upwards and moving up the screen. That's what you can see on the right there. You notice it isn't slowing it down because the force is acting at right angles to the velocity. If we now look at when the particle is heading up the screen, we use the right-hand rule again with our thumb pointing upwards, our fingers are still pointing into the screen, and we see that the force now acts to the left. So it curves the particle's path again. If it's up near the top of the circle, we have our thumb pointing to the left now because the particle's moving to the left, and that means the force is pushing downwards. So the force is always at right angles to the velocity and always points towards the center of a circle. That means that the magnetic force is providing a centripetal acceleration, and a charged particle will follow a circular path with a constant speed if it's in a magnetic field. Since it moves in a circle, we can apply the equation for circular motion. So we make our forces equal. The magnetic force equals the centripetal force. So BQV, since it's at right angles, equals mv squared over r. Now we can cross out one of the v's, and we can make r the subject. And then we will find that r will equal mv over q times b. I want you as an exercise now to work out what would be the period t, which is the time to do one complete circle.